Okay, the next problem that was requested for today was problem number 11, which is a series solution problem. Before when I wrote it out, I had missed the initial condition, so I had to go back and get it. But we're going to go ahead and start from that we want y to be the series Cn x to the n for n from 0 to infinity. That means our y prime by the power rule is just going to start from 1, go to infinity, Cn times n x to n minus 1. And then we're going to plug this guess for y into our ODE. So 0 is equal to x plus 3 times y prime. Plus 4y. And we just want to simplify this until we have something that can represent a single series with the same lower bound and power x. So first I'm going to distribute this x plus 3 across my series. And my last term stays the same. And then I can move this first x inside the series. And then my x to n minus 1 just becomes x to n minus 1 plus 1, or x to n. And then I can see that this last one is also x to n, so I'm going to need my middle series to turn to power x to n. So I'm going to go ahead and do that in this line as well. So I want to end up at x to n. That means I had to add 1. So all my n's become 1 more than they were. So Cn plus 1, n plus 1, and then x to n. And then I have to change my lower bounds. Some of you all have noticed this pattern that you just go down when you increase inside. I like to just check it manually. So before, when I started from 1, my first term was C1 times x to 0. So here, if I plug in 0, I'll get C 0 plus 1 is 1 times 0 plus 1 is 1 times x to 0. Okay, so now all my powers x are the same, and all I have to do is get these lower indices to match. And so since I have 2 at n equals 0 to start, I'm going to go ahead and change this first one to also start from n equals 0. Since before it started at 1, the term I introduce at 0 is like extra. I need to cancel it out. So I'm going to just subtract that C0 times x to 0 that's introduced when you plug in n equals 0. In this case it's 0, so it's just going to go away, but you should be careful because sometimes that term actually will matter. And now I can go ahead and combine these all into one series. So I've got that they all start at n equals 0 and go to infinity. And then I've got Cn n plus 3 Cn plus 1 times n plus 1 plus 4 Cn all times x to the power n. And if I want this to be equal to 0, I need the part in square brackets to be equal 0, because that has to be true for any value x I plug in. And when I'm covering all these different powers, it's really only possible if the coefficient is 0. So I need 0 to be equal to Cn times n. Oops. I'm actually going to go ahead and combine these Cn terms together real quick. So that's n plus 4 Cn plus 3 times n plus 1 Cn plus 1. Or Cn plus 1 is going to be minus n plus 4 over 3n plus 1 Cn. And I'm going to copy this to take to the next slide. When you're doing it in WebWork, and this isn't something that's like important for the exam, but if you want to be getting the right answer, you do have to format this the way that they're expecting to see it. So for them, they're expecting to see an in terms of an minus 1. The way you do this is just by subtracting 1 for all your n's. So that's how I take n plus 1 to n. And then I do n minus 1 plus 4 here over, oops. I cannot write straight today. Okay, that's not a me problem, that's a tablet problem. There. Okay. N minus 1 plus 4 over 3 times n minus 1 plus 1, a n minus 1, or minus n plus 3 over 3n, a n minus 1, when I simplify it. After you do that, you're asked to find the first few coefficients. Since we're given the initial condition y of 0 equals 2, we know that that first unknown coefficient a0 is 2. Remember, that's because y is a0 plus a1x plus a2x squared, so on and so forth. And so if I plug in y of 0, all that's left over is a0. And if that has to be equal to 2, that means that a0 is 2. You all do get lucky on WebWork sometimes. All the numbers are the same, so you can just go ahead and plug stuff in for coefficients, but it's good to know why it works. And then I can solve for a1, which is going to be the case where n equals 1. So it's minus 1 plus 3 over 3 times 1 times a 1 minus 1 is 0. So that's just minus 4 over 3 times a0 is 2. We're asked to calculate up to a3. So I'm going to go ahead and do a2 for n equals 2. It's going to be minus 2 plus 3 over 3 times 2 times a2 minus 1 is 1. So that's minus 5 over 3 times 2 times a1, which was minus 4 over 3 times 2. And then a3 is going to be minus 3 plus 3, because we're doing n equals 3, over 3 times 3, a2. So that's minus 6 over 3 times 3 times minus 5 times minus 4 over 3 times 2 times 3, all times 2. And just plugging in those numbers is enough to get the next few boxes right, but then we are asked to try and write a general formula for what an would be. And in that case, we have to look at the pattern that seems to be developing here. So I'm going to pull out that I have a minus 1 there, and then up top I've got 6 times 5 times 4. And then on bottom, let's see, 3, 3, 2. Yes, I've got 3 to power 3, and then a 2. And I'm going to go ahead and just note, well, I won't do that because for your numbers it might not cancel out so well. So I'll just leave that 2 there for now. And then for my A2, the negatives didn't stay because they canceled out with each other. So I've just got sort of minus 1 squared. 5 times 4 over 3 squared times 2 times 2. And then here I've got a negative that stuck around. There we go. And then I just had a 4 over 3 to power 1. And no 2, so that's a problem for me. Okay. So they only had me stop at 3, but I actually need to go one further to see the pattern because I thought this 2 was like special, but it's actually making like more of a factorial type thing. So I'm going to go ahead and do 4 now. I've got minus, for n equals 4, 4 plus 3 over 3 times 4, A3. So that's going to give me a minus 7 over 3 times 4, which gives me a minus 6, minus 5, minus 4. 3 times 3 times 3 times 2 times 3, all times 2. My minuses all cancel out. So again, I've got minus 1 to an even power. So that one right there was a minus 1 to power 3. And then I've got 7 times 6 times 5 times 4 on the top. So that factorial thing seems to be working right. And then here, the thing that I thought was increasing powers of 3 only in a 2, I can actually see now I've got 4 times 3 times 2. And before I had 3 times 2, and then I had 2, and then I just had 1. So I've got a factorial coming out of here. So if I 4, 3, 2, that leaves 1, 2, 3, 4 3s. And so now I can see before I was having like a 3 times 2 and a 2 and a 1. And so what I seem to have is on bottom, I've got like an n factorial. That's my 4 times 3 times 2 for n equals 4. And then on top, I do 7 factorial when I'm at 4. So I've got n plus 3 factorial. So when I plug in 4, that starts from 7. But I never include my times 3 times 2 in there, or just my times 3 if you consider my initial condition. But so I'm going to divide by 6 to correct for that, because n plus 3 factorial would include times 3 times 2. So I'm divided by 3 times 2 to cancel that out. And then on bottom, I also take a power 3 for whatever n I'm at. So at 4, I had 3 to 4. At 3, I had 3 to 3. And then I multiply it all by 2. That's my A0. And then because the sign switches and it's negative for odd values and and positive for even n's, it's going to be a minus 1 to power n. That goes minus 1 plus 1 minus 1. And that should be your general formula, an. At the end, they ask us to write the solution as an infinite sum. And so in that case, you're asked to fill in this box. So that's what your web work looks like, but actually it just goes right back. That's your coefficient. So our infinite series, when we wrote it down to start, was y is the sum n equals 0 to infinity cn times x to the n. And then at this point, what you've done is you've found the formula for cn, so you just go ahead and plug it in that box that follows that format. And that should be the end of that problem. I'm just going to tell you all, if a series is on your exam, you don't have to worry about the formatting, like, this thing where you have to make sure that the indices are exactly the way WebWork expects to see it. Or you've had a couple where it asks you, like, pull out C0, leave C1 in. Don't worry about that. Just calculate your coefficients the way they are. And so hopefully it's a little easier than it feels like it is on WebWork.